Hey, welcome to Let's Get to the Marks. I'm going through the GCSE Combined Science Trilogy Higher paper. This is a physics paper from 2022. This will take you an hour and 15 minutes if you want to do it like that. And questions, there are 6 questions. What I suggest is at the start of each question, you make sure you've got a pen and paper in your hand. Make sure you have a calculator because it's physics. You're going to need to do maths. And you have a go at the question after I've read through and explained the question. You have a go at it, and then you unpause the video and you watch me go through the explanation. Okay, I'll put a few reminders out, and don't forget to hit the like. Massively helps me out for these walkthrough videos. And good luck with your exams. Let's go. Question 1. Figure 1 shows some energy resources used to meet the demand for electrical power in the UK on one day in 2020. And you'll see over here on what we call the y-axis, the left-hand part of the graph, it says electrical power in gigawatts, and it goes all the way up to 35,000. And then we have time of day at the bottom. So it starts from midnight, then 4 a.m., 8 a.m., midday, 4 p.m., 8 p.m., midnight. Then we have a black line here, which is demand. That's how much energy or electrical power is needed in total over here. And then we have different types of fuels that supply that. So we have gas, this dashed line, nuclear, this solid black line, wind, and then right down the bottom, barely visible, this little dashed line represents coal. Let's get down, look at a question, and we'll probably come back up to this graph to do it. So the question is, the maximum demand for electrical power on that day was at 6 p.m. So at 6 p.m., we got the maximum amount of energy used. Determine the percentage of the maximum demand for electrical power that was generated using gas. It's worth 3 marks. You need your answer as a percentage. What I want you to do is to grab your pen, grab your paper, grab your calculator. It's a little calculation you've got to do. Why don't you press pause on the video now, study the graph, see if you can work out what percentage of the maximum demand at 6 p.m. was gas, and then check how many marks you get. All right, pause the video. Right, now I'm going to go through the explanation. So what you're going to do here, folks, we are going to bust out a little line. We're going to find 6 p.m. Now that's 4 p.m. and 8 p.m. So bang in the middle is 6. They asked us to find out what percentage gas is of the total. So I need to find out what the maximum amount of gas was at 6 p.m. being used. And it's right over here. You can see bish bash bosh. Now we've got a little tricky bit. You have to work out what that number is. That's 15,000 to 20,000. That means there's a value of 5,000. But how many baby squares? How much is each little square worth? Well, there's 10 little squares. So I'm going to divide by 10. What is 5,000 divided by 10? Is 500. So it looks like each tiny square is worth 500. So we go 15,500, 15,000, 16,000, 16,500. So over here, this is 16500, 16,500. That's probably the hardest bit of this question was reading that. Okay, let's go and find out what the maximum demand was of all the energy. We're going to do a straight line. I'm going to come up from here because we're still at 6 p.m. We go up here. Oh, this is lovely and easy to read off the graph. It's 30,000. So our two numbers are 16,500 and 30,000, and we want to find out how much of the 30,000 as a percentage was gas. So what we need to do is this little sum, which hopefully you can work out what you could do. 16,500 divided by, let's just check, that is 30,000. Yep, 30,000. And then what we want to do is times 100, and that is going to give us our percent. What do we reckon that is? 16,000. Oh my days. Let me get my calculator on. 16,500 divided by 30,000 times 100. This is 55%, folks. So if you got that, you get 3 lovely marks. So how do you get these marks? Well, if they see lines on the graph, like at 6 p.m., a line drawn up and a line across, and an attempt to read this off the graph, you're going to get a mark. If you manage to do this sum and then get that, you're going to get all the marks. But you'll just get 1 mark for attempting to draw lines on the graph and show your working where you've tried to read off the numbers. Okay, let's move on. This graph work's really important. It might not seem it, but you're going to every single exam, whether it's physics, chemistry, or biology, you have graph work. So it's worth practicing it to get really skilled at it. 1.2, the UK government wants to reduce carbon emissions as much as possible. Which energy resources need to be used less to achieve this? So they want to reduce the amount of carbon emissions. What do we mean by carbon emissions? Which ones do you have to stop using if you don't want to release carbon? Pause the video, have a go. All right, I'm going to go through the answers. Carbon emissions essentially means let's stop releasing CO2. Which of these cause CO2? Coal and gas. Yep, we don't want to use coal and gas. Both of these release CO2. Nuclear does not release CO2. Wind does not release CO2. Wind and nuclear, this one doesn't release any CO2. So these are all wrong. We need to cut down on coal and gas. Both of those release CO2. They are fossil fuels, and burning those releases carbon dioxide. Okay. 1.3, a network of transformers and transmission cables transfers electrical power from power stations to consumers. What is this network called? So this is a network of cables and transformers. And what do we call it? Hopefully you know this. It's just one you need to know off by heart. It's called the national grid. Okay. And that'll get you a mark. And if you don't know it, why don't you put it on a revision card? And then you can learn it off by heart, along with other things that you don't know that are just memory recall. 1.4, explain how using step-up transformers makes the network efficient. Right, I'm going to do a little drawing of the national grid. Okay, guys, let me go through how the national grid works. So this is my little power station. I know what you're thinking. How did I only get a level 3 in GCSE art? I agree. The examiner should be sacked. I am a proper artiste. Check this out, Mr. Van Gogh. These are my step up and step down transformers. Okay, so what we have here is a power station that is making electricity or making power with 25,000 volts. Now, you might remember that power, and if you don't remember, it's on your equation sheet, power equals current times voltage. So if I have 25,000 volts and I have 1 amp, I can send power 25,000 watts. So power is measured in watts, current is measured in amps, and potential difference or voltage is measured in volts. So I can send my power as either voltage or current or a mixture of both. The problem is high current generates heat. And if you generate heat, you're going to lose heat from your cables on the way to people's houses. You're going to lose heat to the environment as it goes from a hot area to a low area. You're going to lose energy. And this is going to mean you don't have efficient energy transfer, and we don't get a lot of power at people's schools, houses, hospitals, etc. So what we want to do is use a high voltage. We can do that. So you could have 1 amp and 25,000 volts that's made here. That would be 1 times 25,000. You get 25,000 watts. We can step up the voltage until it's like 400,000 volts. Now, if I do that, I don't have to use a lot of current. I could use hardly any current, maybe 0.1 amp and 400,000 volts. I'm going to get 40,000 watts going to someone's house, which is a lot of power. So I can use a small current with a very high voltage and still deliver lots of power to people's homes. Of course, that's what the step-up transformer does. It increases the voltage so that we do not lose heat from having a high current. When we get to people's homes, we actually need a high current to make your laptop work, your TV work and stuff. So what we do is we step the voltage down. The voltage goes down to like 230 volts, and the current obviously goes up, and it will still equal 400,000 when you do I times V. So the current goes way up, and you can deliver current to lots of people's houses. And there you go. It's a way of transferring power with a low current so you don't lose heat. And that's what we need to write here. So explain how step-up transformers make the network efficient. We say they increase the potential difference. Now, we can say voltage because that's the unit of potential difference. So you could say voltage, and that will get you 1 mark. So they increase the potential difference. They're actually very high potential difference, 400,000. This means they can use a low current, very low current, just a few amps. And why does that help? This means less energy losses as heat to the surroundings. And there we go. You're not going to get your cables catching on fire, and you're not going to lose heat to the surroundings. And those are your 3 marks. Wunderbar! Right, let's move on. That's the end of question 1. How did you do? Let's go. Okay, question two. A student made measurements to determine the specific heat capacity of vegetable oil. Figure 2 shows the equipment used. They've got a joule meter, an electric heater, an empty beaker, a thermometer, and a top pan balance. Describe how the student could use the equipment shown in Figure 2 to determine the specific heat capacity of vegetable oil. Well, let's get on and do that as some bullet points. Why don't you grab a pen, grab some paper, see how many marks you can get. You want to calculate the specific heat capacity. What I suggest you do is a little clue before you have a go. I'm going to write down the equation. You'll find this in your equation sheet. Oh my gosh, I can't speak. So you've got the change in energy, sometimes shown as Q equals MC delta T, which is what I prefer, but often in AQA they use this. M is mass of your liquid. You've got triangle means change. So this is change in temperature. Why they don't, oh, actually they don't use a triangle in AQA on their equation sheet. They use this theta symbol, which are just, again, I think they're stupid, but that's just me and AQA, between me and them. And that is temperature. So what does this stand for? This means energy is equal to mass times the specific heat capacity times the change in temperature. A student made measurements to determine the specific. So if I want to find out C, what would you do? What would you need to record? Explain how you would do it to find C. Okay. Pause the video, have a go. Right, I'm going to go through the answer. So first of all, at some point in this practical, you're going to have to rearrange this equation so we can explain what we got to do. And it says explain how they'd use the equipment to determine the specific heat capacity. Well, I'm going to need to divide the energy by the mass and by the change in temperature, and that will give me C. So you guessed it. We're going to have to, what am I doing, dude? Right, there we go. I hate this symbol. That is change in temperature, and that equals C. So we're trying to find C, the specific heat capacity. So I need to calculate the energy. Guess what's going to do that? And I need to get the mass. Guess what's going to do that? And I need to get the change in temperature. Guess how we're going to find that? Let's piece it all together and let's go. So first up, I want to measure the mass of beaker on top pan balance. Okay, so I'm going to measure the mass of the beaker on the top fan balance. Add, I don't know, 50 centimeter cubed of oil. So I'm going to add 50 centimeter cubed of oil to the beaker. I'm going to say using a measuring cylinder. Now measure the mass of beaker and oil and minus the mass of beaker to find the mass of oil. So I want to know what the mass of the oil is, and I've basically explained how to do that. Of course, if you want to be really funky, I'm going to have to write in another color as well to fit it all in over on this black part of the paper. I'm going to say you could zero the balance, I can't spell, before using. And what does zero mean? That means you press a button on the balance, often it's T-A-R-E, tare. You press that button and it goes back to zero. It makes sure that it's zero at the start. So it's just a little bit about your accuracy. So why did I measure the beaker beforehand? Let's say the beaker was 15 grams. I then add 50 centimeters of oil. I weigh it. It goes up to 65 grams. I'm then going to take away 15 and I'll know I've got 50 grams. So I need to find out how much oil is in the beaker. So I need to know the weight of the glass of the beaker or the mass of the glass of the beaker. And we're going to say using the balance. And when I say balance, I mean the top pan balance. Yeah, over here. Okay, so we now have our mass of oil. Now what we're going to do is place, or I'm not going to say place, let's not get poncy. Let's go use the, oh gosh, I'm writing in pink, never mind. Use the thermometer to measure the initial temperature. So we want to measure the initial temperature of oil, right, at the start and record. So you're going to get this starting temperature of the oil. Then what do I want to do next? Next, I want to place on the electric heater and switch on for 5 minutes. So we're going to switch it on for 5 minutes. Take the final temperature. Take the final temperature with the thermometer, obviously, but I'm running out of room, and find the change in temperature. Now, you could write, if you have the room, how to do that. You would take the final temperature minus the initial temperature gives you the change in temperature. So if I wanted to explain that to the examiner, I would say like, oh, geez Louise, let's not do it in black. Can't see that. All right, let's go final temperature minus the initial temperature, the starting temperature, gives me theta T, the change in temperature. We already got the mass, right? We already got the mass, we got that. And now what do we do with this bad boy over here, the joule meter? I want to say um, read how much the energy changed or was used on the joule meter. And then what I want to finally say is use this equation to find C, the specific heat capacity. Now, what we might want to say here is then repeat 3 times, uh, then repeat again um, using new oil, etc. Let's go 3 times and take a mean C. Find the mean specific heat capacity. So I want to do it 3 times again using oil. I could use different masses of oil. It doesn't really matter. The specific heat capacity should work out the same each time. And there we go. That's going to get me 6 bird marks. 1, 2, 3, 4, 5, 6. Boom. Right, let's move on. Oh my gosh. Give one risk when using the equipment. Guess what, peeps? What we got up here? We got a heater, electric heater. What do you think could happen? You could burn yourself. So be careful with the electric heater. You could burn yourself. Let's say burns from the electric heater. Now, did it ask me for a precaution or safety? No, it said give one risk. It didn't say state a safety precaution. So I don't need to say wear gloves, switch the heater off, allow it to cool, be careful. I don't need to say any of that. Okay, that's going to get us the mark. Lovely, because it just wants the risk. That is the risk. We could reduce it by taking some safety measures, but they haven't asked that. A different student did not have a joule meter and calculate the energy transferred by the electric heater. Use the physics equation sheet 2.3 and 2.4 to answer the following questions. Write down the equation linking energy transfer, power, and time. So if you don't know E, you could do it by power and time, and you'll look this up on your equation sheet, guys. You're given the equation sheet, so I'm just going to give you this. It's a free mark. Isn't it beautiful? Energy is equal to power times time. Isn't that incredible that they just give you a free mark in physics when you have that on the equation sheet? But there we go. Let's not go on about it. Being a biologist and a chemist more, I just think it's unfair, but there we go. The electric heater had a power output of 50 watts. Calculate the time taken. Calculate the time taken for the electric element to transfer 4,750 joules of energy to the vegetable oil. So with these, I'm not interested in the story. I'm just interested in what numbers they're giving me. And if you know the units, like energy is joules, power is watts, time is seconds, and look, they want S, they want seconds. We've been given joules and watts, so we should know what to do. We've got 50 watts, that's P. We got 4,750 joules, that is energy. And I know from this, I've got to rearrange it. So how am I going to isolate T, time on its own? I'm going to divide both sides by P, and I'm going to get E over P equals T. So you're going to get 1 mark for that. Isn't that beautiful? 4 marks, this. And then we just smash the numbers in. So we're going to go 4,750. That's the E. And I'm going to divide that by 50. And that is going to give me the time. And what do we reckon that is? 4,750 divided by 50. Gosh, we're going to get 95. And the answer is 95 seconds, folks. That is absolutement beautiful. Right, let's move on. Don't forget, guys, make sure you hit the like, you chip out the video for a second and hit the like if you're finding it helpful. It massively helps me out. In a deep fryer, vegetable oil is heated by an electric heating element. Food is then cooked in the hot vegetable oil. Oh, fried chips, lovely. The deep fryer contains, or samosas, they're pretty good too. The deep fryer contains an electrical component to monitor the temperature of the vegetable oil. Figure 3 shows how the resistance of the electrical component changes with temperature. So we've got resistance on what we call the y-axis, and on the x goes across. Think of a cross is an X, sort of, goes across. That is that axis. We've got the temperature. Okay, what are they asking us to do? They want us to analyze the graph, obviously. What electrical component is used to monitor the temperature of vegetable oil? So think about all the components you know in circuits, i.e. filament lamps, switches, bulbs, diodes. Which one of those components, there's a whole load of them, about 20 you have to know, do you think is to do with temperature? And if you look at the graph, the clue, temperature and resistance. Temperature and resistance. Why don't you pause and have a go? All right. The answer is a thermistor. Thermistors are temperature sensitive resistors. So anytime you have a fridge which has a set temperature, you're going to open the door, the alarm's going to go off. That's your thermistor that's controlling that. You got your iron when mum or dad's ironing your school uniform. If they leave the iron on, it's going to switch itself off and things like that. That's a thermistor. So cool. Um, let's move on. Right, let's move on. The electrical heating element in the deep fryer automatically switches off when the vegetable oil reaches a certain temperature. Figure 4 shows how the temperature of the vegetable oil changed after the deep fryer was switched off. So after it was switched off, the temperature still going up, and then it levels out. Okay. Um, no, after it was switched on. Oh, that's a total different meaning. So figure 4 shows how the temperature of the vegetable oil changed after the deep fryer was switched on. So someone switched the deep fryer on, the temperature increases, getting hotter, getting hotter, getting hotter, and then stabilizes here just above 150, whatever that is, 160. Determine the resistance of the electrical component when the electric heating element automatically switched off. So they're saying determine the resistance, use, and this is the big, big fat clue. They just want you to analyze graphs. Use figure 3 and figure 4. That is the key instruction for an easy 2 marks. When it was switched off, how do we know when this is switched off? We can tell it was switched off here because have a look. It's stabilized. Okay, so determine the resistance of the electrical component when the electric heating element automatically switched off. So it's here, and we know the temperature is 160. So you're going to get 1 mark for realizing at a temperature of 160. And if you've graffitied on the graph, it will help you. You're going to get a mark there. And then I'm going to need to scoot up to the next table. And we're going to look across when the temperature is 160. What is the resistance? Horror my days. Let me clear the screen. So when the temperature was 160, now we've got a little graph here. You've got to work out what's going on here. You've got 50 and you've got 10 squares. So 50 divided by 10. Each baby square is worth 5. So that is 150. So 160 is here. So I'm going to draw a straight line up. And this is testing you on your ability to analyze graphs. Some people find this stuff hard. You draw a line straight up to the curve and then you draw a line straight across. And what they were doing is you got the 160 from down below, so you knew where to look on the graph. And then what is this? And actually, my line's a little bit out, but it should be there. The 2 cubes up. Ken, I need to work out how much each cube is worth here. So what are these? We've got 200 divided by 10. Jeez. So there's 10 baby squares. So each square is worth 20. So each square is worth 20. So that is going to be 240. And its resistance. So it's ohms. That is our answer for 2 Batman marks. All right, let's move down. Boom, boom, boom. Here we go. So we want to say, oh, Sugar Ray Leonard. Right, the temperature was 160 degrees. The resistance equals 240 ohms. Actually, we don't need to write the unit because they got it right there. So 2 marks for the 200. Even if you just put 240, you get the 2 marks. All right, you get the idea. Let's go, people. Let's go. Go, 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 go. Question 2 continues here. Some chips were put in the deep fryer. In the deep fryer, water in the chips underwent a physical change and became steam. So we have some water in there, and that water has become steam. What is this physical change? Why? Oh, I said, what? Why is this a physical change? All water can change to steam. No chemicals are involved when water changes to steam. The change from water to steam can be detected visually. The water will recover its original properties if the steam is cool. Why don't you pause the video and have a go? Okay, so this is a physical change. Now, we used to teach people that physical changes can easily be reversed and chemical changes can't. But of course, with Le Chatelier's principle and all that, you learn about reversible reactions. So there are reactions that can be reversed quite easily. So that's sometimes they used to say, oh, it's easy to reverse. And that's kind of what they mean. You can go back from a gas back into a liquid. If you evaporate, you can condense them back. So let's see which answer sounds like that. All water can change to steam. I don't like that. All water can change to steam. I don't know why I don't like that. No chemicals are involved when water changes to steam. Water is a chemical. The change from water to steam can be detected visually. Yes, but so can a chemical change, right? You see copper sulfate, anhydrous copper sulfate is white. It goes blue. You've got all. So yeah, that's not it. The water will recover its original properties if the steam is cooled. Yeah, if you heat it and then cool it, it will go back to water. So this is a more funky way of saying that. You can condense it back to water, and that is the mark. Okay, question 3. A trampoline is made from a sheet of material held in place by stretched springs. Figure 5 shows a child on a trampoline. You can see the child here in the air. This is called position A. They're up in the air. They've obviously bounced off the trampoline. We have a sheet of material underneath. And then the child at position B has hit the trampoline and it's stretched downwards and the springs have stretched out. Let's see what the question says and then let's have a go. 3.1. Position A shows the child's maximum height above the trampoline. Position B shows the lowest position reached by the child when landing on the trampoline. Describe the changes to the stores of energy of the child, the springs, and the surroundings as the child moves from position A, so that's up in the air, to position B when they hit the trampoline. Um, so we need to describe the child. They've given us more writing for the child. I suspect out of these 4 marks, it's 2 marks for the child, 1 mark to talk about what happens to the springs, and 1 mark for the surroundings. And all of our answers need to be in the terms of stores of energy. So the 7 stores of energy that you need to know. And if you don't know them, stick them on a revision card so that you can learn the names of the 7 stores of energy. I'm going to go and answer this up here and let's go for it. Okay, at position A to position B, what energy store changes in the child? So I'm going to write my answer here rather than down below. Let's check it out. So I'm going to say the child. Oh, by the way, pause the video. Have a go, folks, on a bit of paper with a pen, and then unpause and I'll go through it. All right, the child has GPE. Now, you're not allowed to use abbreviations, but I am, which decreases um, as they fall. So as they fall from position A to B, and I didn't even need to write that. It already told us you're talking about between position A and B. I could have just said gravitational potential energy decreases. GPE decreases. That's going to get me a mark. Just saying gravitational potential energy decreases. They're not as high up in the air, so there's less gravitational potential energy stored in their body. Now, as they fall, imagine you drop something. It's moving. What do we call the type of energy that's moving? So we're going to say they gain kinetic energy at first, but then when they hit position B, they've stopped when it gets to the bottom of the stretch. So the kinetic energy goes to zero. So we're going to say they gain kinetic energy, then it drops to zero at position B. Okay. And that's the 2 marks for the bit to talk about the child. Now they've asked us, hey, what about the springs? What happened to the springs? Have a look. The springs get stretched. What type of energy do you get in things like springs or elastic bands? You get elastic potential energy. So we want to say the elastic potential energy of the springs increased. And that is going to get you the 3rd lovely jubbly mark. Now, the 4th mark was to say what happens to the surroundings. So what we're thinking about with this child is as they fall, how is some energy transferred to the surroundings? There's probably a bit of a noise. So sound is radiated away, but we've also got heat being radiated away or escaping. So we want to say some energy is lost as thermal energy, whoops, to the surroundings. And any object that's moving, you're going to get that. Most extreme is seeing spaceships re-enter the atmosphere and they all burn on the outside of them during re-entry because of all the heat that's being passed to the surroundings due to friction. Okay, so we've got our 4 marks. Absolutely beautiful. All right, let's move on. So that was the answer that goes down there. Now we're going to go to 3.2. We've got a calculation. When the child is at position A, each trampoline spring is stretched by 0.056. The elastic potential energy of each spring is 4.9 joules. When the child is at position B, the elastic potential energy of each spring increases to 8.1 joules. Calculate the extension of each spring when the child is at position B. Okay. Let's find that equation sheet, peoples. So, hold on. Here it is. Okay, so here's the equation sheet. You can see physics equation sheet, GCSE Physics. I know we're looking at combined, but the equation is going to be definitely on here. What have we got? Elastic potential energy is equal to 0.5 times the spring constant. Let me zoom in on that so you can see that. Elastic potential energy is equal to 0.5 times the spring constant times extension squared. You might say, how do I know to pick out this equation? Well, they've talked about the springs, right, in the question. They've talked about extension And so we're going to need, and they've given us the elastic potential energy. So we know we've got to use this, and we don't know K, the spring constant. Let's go back and see if we can crack this question. Okay, so we're going to go back to the question. Here we are. When the child is at position A, each trampoline spring is stretched by 0.056 meters. So what is that? That is telling me the extension, E. The elastic potential energy of each spring is 4.9. That is the energy. When the child is at position B, the elastic potential energy is 8.1. Calculate the extension at position B is 5 marks. Why don't you pause the video, have a go? Now, we're going to have to start off by working out, look, this spring constant. You might say, why? Well, we know energy is equal to K, 0.5 K. Well, they said. I'm copying down what we just looked at, 0.5 K, and that is times the extension squared. So that's our equation. Now, I don't have, for position B, we've just got E, the energy. We don't, and we're asked to calculate the extension. We can't do that without K at position B. I need to rearrange position B to find K, but sorry, I need to rearrange position B to find lowercase e. And how I do that at position B, I would go, I want to get E on its own. So I would go E for energy, divide the elastic potential energy by 0.5 K. That would leave me with equals E squared, right? What I would then want to do is get rid of this square. So I've got to square root both sides. And that is the working out that will give me the beautiful marks for working out lowercase e, the extension. However, I don't have K. So I have to use this first set of data at A to work out K, and K is constant. It's called the spring constant. So it's going to be constant even at this new position where the springs have been stretched. So let's work out K from the first position. So I need to rearrange this first of all to find K. Why don't you see if you can do that using 0.056 and 4.9? I know that's impossible to see because old idiot head here has drawn all over it, but that's the extension. All right, let's check it out. Let's work out K. So we want to say at A, let's work out K. So to rearrange this, I want to do energy divided by the extension squared equals 0.5 K. Why don't I times both sides by 2 originally? So I'm going to get 2 times the energy divided by extension squared equals K. Let's go ahead and do that. So I'm going to go 2 times so this is going to get me the first 3 marks. 2 times 4.9. By the way, 4.9 is the energy. And that equals 9.8. That's my 2 times the energy there. I'm going to divide it by the extension squared. The extension was 0.056. So I'm going to do 9.8 divided by 0.056 squared. I'm going to go and jam that in the old calculator. And that should get me 2 to 3 marks straight off for working out K. So 9.8 divided by, and here's the tricky bit, 0.056. In fact, let's go 0.056 squared at 0.056 squared, by the way. I'm going to just simplify it so that you can see, because you might want to break it down. You might find it hard to use the old calc. So if you're finding it hard to get the right answer without, you can do the 0.056 squared first. And if you do that, you're going to get 0.0031. Is that a 3 or an 8? 36. Okay. My eyesight is not good. And then 9.8 divided by that. So 9.8 divided by answer. We're going to get 3,125. Now, the extension is in Newton. What do we do? We did 9.8 joules over the so joule meters or whatever that is, Newton meters or whatever. That is the extension, but do we need the units? No, but it's 3,125. That should have scored us at least 2, possibly 3 marks. We now know what K is. So if you're wondering what we've just worked out, we've just worked out the spring constant. I can now go down. I've already rearranged this at the start of the question, and I want to do energy at the new position is 8.1 bish. And I want to do 8.1 divided by 0.5 times 3,125. And then I want a square root, and that is going to give me the new extension of the spring at E. Oh my gosh, they don't want the difference in the 2 extended springs. Okay. Okay, so they just will calculate the extension of each spring where the child is at position B. They don't want the difference. All right, let's do it. Let's do it. Let's do it. Let's go 8.1. And then I'm going to divide that by 0.5 times 3,125. You can break it down if you like. So essentially, I'm going to get I need to square root 0.005184. You can just jam it all in the calculator. You don't need to do this. And then I'll just go square root answer in my calculator, and I get 0.072, and it's already in meters. Lovely jubbly, 0.072, and that's going to get me 3 fat wicked marks. All right, let's move on. Boy, this question 3 is taking time. 3.3 is the child bounces on the trampoline, the child does work. Everybody must work. What is the work done by the child equal to? The average force applied by the child, well, it would be the maximum force applied by the child, the total energy stored, the total energy transferred by the child. Yeah, it's going to be the total energy transferred. I didn't really explain that very well at all, but work done is equal to the energy. Work done is another type of energy. So the child bounces on the trampoline, the child does work. What is the work done by the child equal to? The total energy that they transfer. So if they transfer energy into kinetic energy as they move in the air, and gravitational potential energy, all that has come from the energy in their legs, the work done by their body. That was a crapo explanation, but never mind. All right, let's move on. I tried to look at the equations, but that didn't really happen. All right. Question 4. A student investigated how the pressure of a gas depends on its temperature. The volume of a gas did not change. The figure 6 shows the equipment used. We've got the pressure meter. We've got a thermometer. We've got a mixture of ice and water cooling this bulb, and we've got heat underneath. Okay, pressure is sometimes measured in units called atmospheres. 1 atmosphere is 10 to the 5 pascals. What is 1 atmosphere in kilopascals? So all you've got to do, one atmosphere is 10 to the 5 pascals. What is 1 atmosphere in kilopascals? So 10 to the 5, do you know how to turn that into, not into standard form? So that is going to be 10 to the 5 is 100,000 pascals. Now, what is that in kilopascals? Well, I need to divide by 1,000. The K stands for kilo. So 1 atmosphere in kilopascals is 100 kilopascals, like that. There you go. Lovely jubbly. Let's give ourselves a mark. Right, let's go down. 4.2, the student took 4 pressure readings for each temperature. The table 1 shows the pressure readings when the temperature was 50 degrees. Temperature was 50, the pressure in megapascals, that's not milli, that's a big number, big capital, stands for a bigger number than normal, so megapascals. We've got 0.115, 0.120, 0.121, 0.116. Calculate the uncertainty in the mean pressure. Right, in order to calculate uncertainty, we need to do the range, find the range in the results, and then we need to half it to find how much above and how much below it is likely to be. So what we do is we're going to find the range in the results. What's the lowest number here? The lowest number is 0.115. What's the biggest number here? The biggest is 0.12. So we're going to go 0.121, take away 0.115 equals 0.006. So that there, folks, is the range. That's the range in the results. And then we want to divide that by 2. So the results, the uncertainty is really plus or minus 0.003. And that's how you work out uncertainty. Find the range, half the range, and that gives you your uncertainty. And that will get us 2 lovely marks. Okay, 4.3. Figure 7 shows a sketch of, start that again. 4.3. Wine. 4.3. Figure 7 shows a sketch graph of the results. We've got pressure in megapascals. We've got temperature in degrees at the bottom. This is figure 7. The student said that as the temperature increases, the pressure increases. As the temperature goes up, the pressure goes up. That sounds pretty good, doesn't it? Give a better description of the relationship between temperature and pressure. Ooh, well, that sounded pretty good. So the student said that as the temperature increases, the pressure increases. So what's a better description? I would add the detail that yes, as the temperature increases, the pressure increases, and it's linear. There is no curve. It's a linear increase. It's a straight line. So, it is a linear increase. Okay, so it's not curving. It's not like at a certain temperature, the increase starts accelerating up or decreasing down. It's a linear relationship. Beautiful. Wunderbar, wunderbar. So they weren't wrong. This is just a better description. A little bit of nuance. Right, a pressure cooker is a sealed pot that uses steam to cook food. So we've got some broccoli in here. We've got some steam. We've got water, which is obviously vaporizing, becoming steam. Platform to hold the food. Heater underneath to vaporize the water. Safety valve. When the water in the pressure cooker starts to boil, the amount of steam in the pressure cooker increases. The temperature of the steam increases above 100, so it's superheated above 100 degrees. Explain why these changes make the pressure in the cooker increase. So why do we get an increase in the pressure? And it's worth 5 Badman fat marks. So let's check it out, eh? Okay, okay. I like to think of this one we like to do with the pressure equals force divided by area. So when the steam particles are moving around, they are colliding and exerting a force on the area, the walls of the cooker. Okay, now what happens? We're heating them up. So what happens to the movement of these particles and what happens to the force? And we need to explain all of that. So we're going to say, um, as the steam particles are heated, they gain kinetic energy. They move faster. What does that mean? They collide more with the walls of the container, in this case, the steam cooker. So we get more collisions with the walls of the container. They exert, or we can say, so a greater force is exerted over the area stroke walls on my days of the container. Okay, so what are the 5 marks for? Cheese Louise. The steam particles gain heat, they gain kinetic energy, they move faster. Moving faster means more collisions, so collide more with the walls of the container where a greater force is exerted over the walls of the container. And you can see pressure equals force over area. So greater force over area, it means the pressure increases. I might just want to finish that off by saying bigger force over area equals more pressure. Okay. Wunderbar. I think I've said that a little bit too much. Practice my German. That's just good, yeah. 4.5. If the pressure inside the pressure cooker becomes greater than 200 kilopascals, then some of the steam is released through the safety valve. The released steam expands as it moves into the atmosphere. Explain how a change in density of the steam, I can't speak. Explain how a change in density of the steam is caused by a change in the arrangement of particles in the steam as it is released. So what do we want to say? Released steam expands as it moves into the atmosphere. So what do they mean by expand? So here's my steam, right? Remember, steam is a gas, so the particles aren't touching. They're kind of randomly moving around each other. You get the coup. That's not the best drawing ever. There's my steam. Then it expands. Do they mean the particles get bigger? Of course not. The atoms themselves don't get bigger, or they're not necessarily atoms, are they? They're H2O molecules. Each one of these black circles represents molecules. But what do they mean by expand? They mean that the volume increases. They take up a bigger space. So how is that going to affect? Has the mass of the atoms changed? No. Although I've now added one extra atom. Let's get rid of it. I've got 5 water molecules there. I keep talking about atoms. 5 water molecules there, 5 water molecules there. What has changed about them? The volume. So we want to let the examiner know that we know density equals mass divided by volume. The volume increases. However, the mass stays the same. So what happens to the density? What do you think happens to the density? Let's put an equation in and that will tell us. So let's imagine the mass is 5 originally over here. Let's say the mass is 5 and the density is 2. Sorry, the volume is 2. So if the volume is 2 and the mass is 5, Our D for density is 5 divided by 2 is 2.5. We just said that the volume increased. All right, let's say the volume doubled and it increased to 5. So we now go mass over volume, 5 divided by 5, that equals a density of 1. So what happened to the density? It went down because the volume increased. So that's what we need to say. The volume increases, however, the mass stays the same. So the density goes down. And that's going to get us all three fat bad man marks, especially we put the equation in there and kind of use that to help us. So, yeah. Okay, question 5. The camera in a mobile phone uses an LED to provide light when taking a photograph. A student investigated how the potential difference across an LED varies with the current in it. Figure 9 shows the circuit used. Here's figure 9. Here's the circuit. We've got the LED here, we've got the ammeter, the voltmeter in parallel, we have a battery. Now the word battery, actually one of these is called a cell, and if you have more than one, we call it a battery. So we have a battery of cells here, we've got a switch, and we have a resistor. The student closed the switch. The voltmeter gave a reading of 5. The ammeter gave a reading, I can't speak, the ammeter gave a reading of 0 milliamps. The LED did not emit any light. Explain how the student should have changed the circuit to make the LED emit light. It's worth 2 marks. Why don't you have a think about it? Press pause on the video where you have a think. You could write your answer down if you want, or you could just think about what 2 things could be the reason why this does not light up when the switch is closed. Okay, I'm going to go through the answer, and essentially what's going on here is that we have an LED. This is a light emitting diode. Now notice this little line here. This is telling you it's like a wall. This will not let current go through it. And the current goes like this, even when the switch is closed, and the current is moving around from the plus side to the negative side of the battery, it cannot get past that wall. So in order to allow it to go, what do we need to do? We're going to need to reverse the LED, and that would allow it to go through. So if the LED was actually this way, if that was our LED and it was pointed in that direction, then the current could flow through. But because the LED is that way and the current's coming from this side of the battery round like that, it cannot go through. Let's construct that into a legible answer. Oh my days, how do I get that onto that and move the screen down? There we go. We finally managed it. Explain how the student should have changed the circuit. So they needed to reverse the LED direction to allow current to flow, as diodes only let current flow in one direction. So it was going in, the LED was in the wrong direction to allow the current to flow. They're quite useful when you want to convert alternating current to direct current as well. And this is a special type of diode which emits light energy when the current passes through it in one direction. Okay, 5.2, the student changed the circuit so the LED emitted light. Emitted means gave out. So the LED gave out light. The current in the circuit was 290 milliamps. The power of the LED was 0.98 watts. Calculate the potential difference across the LED. Use the physics equation sheet. Give your answer to 2 sig fig. So we want to work out what these numbers are. Amps, that is actually current, which on equation sheets has the symbol I, and watts is actually power, and they've asked us to calculate the potential difference, which is measured in volts. So we're looking for an equation with P, I, and V, and what we're going to do now is I'm going to flip to the equation sheet. So bear with me, people. Bear with me, bear with me, bear with me. Okay, so here is the equation sheet. Where are we? Here we go. Look at that. Oh no, that's VIR. What a dipstick. Power, there we go. Potential difference, current. They're the ones we had. P equals VI. They want us to find V. So let's go back and smash that down. So they want us to find V, and the equation we're looking at is P equals I times V. If I want to get V on its own, I'm going to do P over I. So I'm going to do this. P over I equals V. That's the rearrangement that we need to do. It's going to get me a mark if I show somewhere in my working out that I've done the rearrangement. The power is 0.98 watts. Now we have an issue here, and that is, you might have spotted it, milliamps. How do I know it's not mega amps? The little m tells you it's milli, it's baby small, and I need to put it back into amps. Now, the weird thing is, the kind of misconception or the counterintuitive thing is that when you go from a small unit back to a big unit, you divide when you go on the way up. You don't times when you go back to a big unit. Think of your height. If you're 160 centimeters in height and someone asked, what is that in meters? Meters is bigger than centimeters. You would divide 160 by 100 to get 1.6 meters. So when you go from a small unit to a big unit, you divide. When you go from a big unit to a small unit, you times. So we're going small unit back to amps. So in order to get back to amps, we're going to, what did I say? I said small to big, we're going to divide by 1,000. So we're going to have 0.98 over 0.290 amps. And I want to show that I did that properly. So 290 divided by 1,000. And that's going to get us a mark just for showing that we did that. Then I'm going to do 0.98 over 290. It's going to get me a mark. Bish, bash, bosh. And then I need to come out with the answer. So let's bust out the calculator. 0.98 divided by 0.290, and that is going to get me 3.379, and that is going to be my fourth mark. 3.379, blah blah blah, loads of other numbers. That's going to be my fourth mark. Now, what's the fifth mark for? Well, have a look, people. Always watch out for this because it's an easy mark to lose if you miss it. Give your answer to two sig fig, two significant figures. So only two numbers, not including any zeros. We don't have any zeros here, so we just want these first two numbers. Because that is 5 or greater, it's 7, which is 5 or greater. We're going to round that to 4, so it's going to be 3.4 volts. And that, my friends, ladies and gentlemen, is going to get us 5 marks. Okay, let's zing. A traditional camera uses a flash unit to provide light. Figure 10 shows a flash unit on a traditional camera. The flash unit emits light from xenon gas in a fluorescent tube. What happens when a xenon atom emits light? Electrons in the atom fall to a lower energy level. Electrons in the atom move to a higher energy level. Electrons leave the atom, causing ionization. Electrons transfer to the atom from an electrical circuit. This one I think is pretty difficult, and I don't think a lot of people know this. So if you don't get it right, don't punch yourself in the face. Okay, but the answer is electrons in the atom fall to a lower energy level. What happens is electrons get excited. You remember when in chemistry and in science, you draw electron shells. Electrons can jump between those shells. You can excite them by heating or various electricity. You can provide them with energy so that they can jump from one shell to another shell, inner shell to outer shell. When they fall back down, the energy levels, they emit the energy they gained as light, and that is why we get different sort of color lights. So the electrons in the atom fall to a lower energy level and they emit light in doing so. If you don't know that, you might want to put that on a revision card somewhere, just like why do some atoms emit light? And you could be electrons in the atom fall to a lower energy level. You could have that as your answer. It's one of those weird ones that rarely comes up, but when it does, it probably catches out over 50% of the students in an exam. So don't beat yourself up if you got it wrong. 5.4, when the flash unit is used, there is a mean potential difference of 200 volts across the fluorescent tube. That's what's exciting the electrons. Okay, the flash of light lasts for 2.8 times 10 to the minus 4 seconds. So what I would do when you're reading one of these maths questions, I would, we've got volts, so we know what that is. There's already a V there. I don't really need to write a V. What's this? 2.8 times 10 to the minus 4 S. That's going to be time. So when I go to my equation sheet, I want to find time. I know I've got V. 1.4 joules of energy is transferred. Right. I'm looking for E for energy. Calculate the mean current. So I want I. So I'm kind of looking for something that has time, current, voltage, energy. Use the equation sheet. It's worth 6 marks. Why? Let's have a little look on that equation sheet and see what we can do. Okay. So we go over to the equation sheet. Sorry, I've got all these things on the screen here. And you can see if we go down to energy, where power is energy over time. So I could definitely find out the power So I might need that. Power is energy over time. What else? What else? Energy. Oh, we've got some more down here. Power equals potential difference times current PVI. Got that in there. EPT, energy transferred equals power times time. I think between all of these ones, we can probably work out what we got to do. Let's go back. Okay. So we're probably going to need more than one equation because it's a fat six marker, but let's have a little look. Okay. More than one way to do that, to do this, but the way that I'm going to use is using these two equations. You kind of know there's going to be more than one equation. When it's 5 or 6 marks, it often is more than one equation. So I know that I've got E and T, and look, E and T are over here in this equation, and then I don't have P, but then P equals I times V, and I've got that and that, and it's asked me to calculate I. Guess what? If I can use this to calculate P, then bust that into there and use that to calculate I. You know what? Why don't you have a go? Pause the video, unpause and watch the explanation. Okay, I'm going to go through it. There's more than one way to skin a cat. There's more than one way to do this, but this is the easiest way that I can think of to do it. So you're going to get some marks for picking some of these equations. So 1.4 is the energy equals P times time, which is 2.8 times 10 to the minus 4. Okay, that's seconds, that's joules over there. What I want to do is rearrange this. How can I get P on its own? Well, I can divide both sides by 2.8 times 10 to the minus 4, and I'll end up with 1.4, which is the energy. So that's the energy divided by 2.8 times 10 to the minus 4. I know what you're thinking. Why aren't I using the units, joules, and that? Well, I'm just trying to like simplify it for you guys. So that's the time. So I'm really from those things that I pointed out there, I'm doing 1.4 over the time, and that's going to give me P. Let's find out what P is. So I need to smash that in the calculator. 1.4 divided by 2.8 times 10 to the minus 4 equals 5,000. So that means that the power P is equal to 5,000 watts. Now I can take this equation, rearrange it to find I. So I want to do, if we divide both sides by V, I'm going to get P over V equals I. I know the power is 5,000. Now I believe they gave us the watts. Let's double check up there. And they did. It's 200. Sorry, the volts. We got the 5,000 watts, the volts. Now, if you're wondering what that is, that's the P that I was banging on about, and that's the V. So I'm doing 5,000 power over 200 volts. That's 5,000 watts over 200 volts. And 5,000 divided by 200, you can probably all do that in your head, but you're not smart enough. And that equals 25 amps. And so you're going to get some fat marks here. Now, you get 1 mark for selecting any of the correct equations like that, 1 mark for rearranging the equation, then we worked out the power, then we're stepping up with the second equation, so you're going to get a mark for that, and then a mark for that. What a lovely 5 marks that is. Okay, let's move on. Last question coming up. Okay, we're on the last question. It would help if I didn't cut the head off it. A smoke detector contains a source of alpha radiation in a plastic case. A source of beta radiation in a smoke detector would be more hazardous than a source of alpha. Why is that? Okay, now alpha is actually more ionizing, so potentially more dangerous. But of course, alpha cannot penetrate the plastic case and cannot penetrate your skin. However, and I've worded this a long way, I know. However, beta radiation, and this is where the marks come in. I could have just stuck with this. Beta radiation is more penetrating, or has higher levels of penetration and range, so it can travel further inward. So it's more penetrating and has a higher range in air. It can penetrate skin. It is ionizing, can cause cancer. Look, alpha radiation is even more ionizing, but it can't penetrate your skin. I'm just telling you why beta is dangerous, because it can penetrate the skin. It has a greater range in air, so it can travel further. Alpha can only go, a few centimeters in air before it's absorbed. The only way that alpha is going to get you is if it gets inside your body, and then it's going to go around knocking electrons off atoms and causing cancer all over your body. Okay, let's move on. 6.2. Ooh, we love a bit of AC. Actinium is one source of alpha radiation. An actinium AC nucleus emits an alpha particle and turns into a francium or francium, depending on how you like to say it, nucleus FR. This can be represented as AC, AZ, 223, 87, and alpha. Determine the values of A and Z. 2 marks. Why don't you press pause on the video? Have a go at this one, and then I'll explain. Okay, you should know this one off by heart. This is just a pure memory recall one. So if you know the alpha symbol like that, you should know that is a helium nucleus, an alpha particle. It has a mass of 4 and an atomic number of 2. So if that is 4 and that is 2, and remember the conservation of mass, everything on this side of the equation must equal everything on that side of the equation with chemical equations. So A must be 2, 2, 3 plus 4. What do we reckon that is? That is 2, 2, 7. And then Z must be 87 plus 2. So we want to do 87 plus 2. That is going to be 89. And that is going to get us 2 lovely marks. Well done if you got it right. Pat yourself on the back. All right, let's go. Teacher wanted, this is 6.3, a teacher wanted to find out what nuclear radiation is emitted from a source. The teacher placed different barriers between the source and a detector. So in case you're struggling to understand what that is, they got a source that's giving out radiation. They started to put barriers in the way, and over here they had a detector detecting whether any radiation got through. The teacher recorded the count for 30 seconds after each barrier was in place, shows the results. When there was no barrier, 985 particles hit the detector in 30 seconds. Why have I drawn over that? Who knows? When paper of 0.1 millimeter thickness was put in the way, 149 got to it. So some has been blocked by paper. Okay, it's giving me an idea of what it might be, because quite a lot were blocked by paper. Aluminium, 5 millimeter thickness, blocked everything. Oh, okay. And lead blocked everything. Okay, so explain what nuclear radiation was emitted by the source. 4 marks. Okay, it's not straightforward, but you should be able to pick up some marks here. Pause the video, have a go. All right, I'm going to go through the answers. So here we go. Alpha radiation is blocked by paper, as a lot is blocked, or what I should say, as the count falls, when there is a paper barrier, some of the source must be alpha, right? Beta would get through that paper. It's only 0.1 millimeter thick. So if it was all beta, all 985 would get through that. This suggests to me that some's got through the paper, and maybe that stuff that's got through the paper is beta or gamma. Let's decide what it is. So, and then we want to say beta has higher penetration, can get through paper. However, gamma would go through all the barriers except thick lead. So the other source must be beta and not gamma. So basically, what I've tried to say here is it's giving out beta and alpha. Why is it giving out beta and alpha? Well, we can tell it's giving out alpha, mostly alpha. It's like 90% alpha, because 90% of it got blocked by paper, and alpha radiation is blocked by skin, blocked by paper, even blocked by quite a distance of air particles will block alpha. So that's blocking the alpha. Some's getting through the paper, so that must be beta or gamma. However, if it was gamma, if this 149 or any of that 149 was gamma, it would also get through 5 millimeters of aluminium. So the fact that none of it has got through aluminium or the lead means there's no gamma radiation there, because gamma has the highest penetration. So it's giving out mainly alpha, but also some beta as well. And there we go, 4 fat marks. Okay, we got a graph. Figure 6.4, figure 11, no, not figure 6.4, question 6.4, figure 11 shows how the activity of 4 different radioactive isotopes A, B, C, and D changes over time. Activity in becquerels, BQ. We can see the activity is dropping over time. Nice. Okie dokie. Lovely jubbly. Let's go down to the actual questione. Write the isotopes A, B, C, D in order of increasing stability of their nuclei. Explain your answer. 3 marks. Least stable to the most stable. Explanation. So we want to work out their half-lives. Basically, if you have a short half-life, you are the most unstable. So let's work out the half-lives. Oh, geez. We can work out the half-lives of each one. So why don't you pause the video, have a go, try and work out all the half-lives and then put them in order. Shortest half-life is the least stable to the longest half-life, the most stable. So you see this one here that starts at 400. What I want to do is track how long it took to get to half. So half the activity from 400 to 200. So I'm going to go along here. Oh, look at that straight line. That is an incredible line. And there we go. The half-life of this bad boy is 15 years. And I think it's 2 for 1, 15.1, 15.2, 15. Oh no, there's 10. So what am I on about? 16, 17, 18. No, no, no. I'm right. 15.1, 15. No, 16, 17. Oh my gosh, I am so stupid. So A has a half-life of its half-life is 17 years. Okay, that's the half-life, 17 years. Let's check out B. I'm going to do a different color for B. Um, oh, maybe I should just delete all of that. Yeah, let's rub that out. Okay, guys, let's do B. So B starts at 250. Do you know what half of 250 is? 250 divided by 2 is 125. Let's go down to 125. There's 100. 125 is halfway there. So I'm going to draw there to be hit line B. Let's go down. It's kind of like that is 10, 11, 11.5 years. I'm going to say it's 11.5 years. I might be slightly off there, but it's going to be enough. So its half-life is 11.5. So it's not as reactive. It's certainly less stable than A because A is taking 17 and a half years for half of the isotopes to decay. This is taking 11.5 years for half of the isotopes to decay. Right, I'm going to pick another color. Let's do a lovely green. And we're looking at C. Oh my God, I can't do C because C hasn't even fallen 50. So C, let's check out the half-life of D. D is a bit easier because it's 150. I want to go to 75. Oh my gosh, I wish I could draw a straight line. I should just bust out a straight line. All right, I don't know what that is. That is 6, 7, so about 7 years. So looking at D, D looks like the least stable. Yeah, D's the least stable. D's half-life is, what do we reckon for D? D's half-life is, oh my God, look at it, half-life, 7 years. So out of A, B, and D, 7 years, got a feeling C, folks, is the most stable. Check it out, it barely moves. How many years? It starts at 100. After 20 years, is it at half? It's not at half. It's not even down to 50. So C has a big fat half-life. In fact, if we sort of carried it on and made a prediction when it would hit 50, be somewhere like over here. It's like got a 35-year half-life. So C is the most stable. I don't know if you can see that. C has the shallowest or least steep gradient. It has the biggest half-life. So is most stable. And then we would want to say D has the lowest half-life, is least stable. So boom, boom, boom. My order is going to be C, A, B, D. C, A, B, D. And that is going to get you all of the marks. Let's go down, check it out. C, A, B, D, and there's my explanation. So I put them in order of their gradient and order of their half-life. So that's what I would say for the explanation. And that, guys, is the end of the test. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll catch you lot on my next walkthrough.
You're still here? It's over.